Hi guys, welcome back to our third of three videos for lesson number one in AB Calc, which is limits to infinity. In the previous two videos, we talked about finding limits of rational functions where the numerator and the denominator both were polynomials, and we talked about looking at the highest degree of the denominator and the numerator and comparing the two. In the last video, we talked about parent functions, making sure you guys know how to graph them and looking at the end behavior model, so what's happening at positive and negative infinity as x goes positive infinity, negative infinity. We talked about transformations of our parent functions. What does it mean to do plus 5? What does it mean to do negative 3? In this example here, I talked about how I can split it up and do individual pieces, and you can absolutely do that. We talked about polynomials. We looked at whether it's an odd polynomial or an even polynomial, and then if the leading coefficient was even or odd, and what to do with those examples. And then we did a very simple example with sine of x, where if a limit is oscillating to positive or negative infinity, the limit will simply not exist. So in this video, we're going to talk about square roots, and then we're going to talk about rational functions that do not contain polynomials. So for this example right here, it says given f of x equals x over the square root of x squared minus 16. I want to just say really quickly that this function still is technically polynomials. The highest degree in the numerator is still an x, but the highest degree in the denominator is actually x squared, but it's underneath the absolute value. Sorry, it's x squared, but it's underneath the square root. Got a little ahead of myself here. So this is my side work. So I'm going to do x over, and then I'm going to go ahead and do the square root of x squared. So let me just say really quickly that if I'm taking the limit as x approaches positive or negative infinity, so let me just say something about why do I care about just the highest degree in the numerator or the denominator. So let me just give you guys an example of something like this. So if I tell you guys that the limit is x approaches infinity of x cubed minus 5 over x cubed plus 5, and I want this limit, you guys know this limit is 1. You know that the highest degree in the numerator and the denominator are equal to each other, so the leading coefficient is what you do. Why can't I just throw off the negative 5? So here's the analogy I use in class. I give you $1 billion, and then I then cube that, right? So 1 billion cubed. That is a huge, huge, huge number. In the whole grand scheme of things, if I give you $1 billion and then I cube that amount and I hand that to you, you're not, and some people maybe, but most of you are not going to mind. It's like, okay, now can you give me $5 back? It's not going to matter to you. Or if you got $1 billion and you cube it and I hand you another 5, it's not going to make that much money. It's not going to make that much deal for you, right? We're not going to care about it. So when I'm looking at something raised to infinity and I have minus 16, so I'm taking infinity and I'm squaring it, if I ask you simply to subtract 16, we're not going to care. So we can now say, well, let's look at this problem a little bit more. So let's actually clarify that this here is still x, and that this square root of x squared simplifies down to the absolute value of x, right? The absolute value of x, because if x is negative 3, I square it, I get positive 9, and then take the square root of 9, I get positive 3. So it doesn't matter if x is positive or negative, I have to take that into account here. Now, if I'm looking at negative infinity, my x values are going to get less, right? We're going to have negative x values. So I'm going to, and again, this is just my side work for this, and this is not actually finding the limits, because if I were, then I would have that limit notation here. We'll talk about that later. So negative infinity over negative infinity absolute value, right? So I'm plugging a negative value for x for this problem, and so this is still negative x, and this is going to be positive x, right? Because the absolute value of anything is going to give you a positive value. And now I can simplify this. I can simplify this and just get the answer -1. So this answer is -1. On the other side of this, I can say that this problem right here, I go back and I'm going to plug in a positive. So I'm going back to this step right here. I can plug in a positive to both the top and to the bottom. Well, positive x is just positive x. It's just x. Positive 9 is still 9. And then the positive value of x and the absolute value, again, it doesn't matter what this is, the absolute value is still going to give you a positive x, and that's going to simplify down to positive 1. Okay, so that's pretty straightforward. I do want to say very quickly, and again, we're not trying to trick you here, if I've thrown a negative in here, right, in this problem right here, then this would be negative, this would be negative, and then this would be a negative, so we can change the signs. So again, I don't want you guys to always think that if it's a negative infinity, this answer is always going to be negative, and it's positive infinity, it's always going to be positive infinity. You really, really, really want to make sure you watch your signs. Okay, so let's look at example number 11. So this is one of those questions where I say maybe you try it for a second, you can pause the video and see what you can do with it, and And of course, you know I'm going to talk about it. So let's look at this problem. And again, this is our side work that we're doing right here on the left. So I have that x squared is the top, and then I've got the square root of x to the fourth in the bottom. And so I've got x squared in the top, and I've got the absolute value of x squared in the bottom. And so, ladies and gentlemen, now this is where I'm going to save a little bit of time. Notice that if I put a negative to any of this, it's always going to be positive, right? And I can just go ahead and just do this because the absolute value of x squared, this is always going to be positive, right? No matter what value I put in for x. So I don't even need to even worry about this. I can just do x squared over x squared, so it's going to be 1. So for positive and negative infinity, it's going to be 1. Now, if it were another value, like x approaches 3, you have to plug in. You have to substitute. And we'll talk more about that in lesson number 3. Okay? So this is only to positive and negative infinity can you do this little work. All right? So there is that problem. So let's do our last little set of limits. And we call these functional dominant problems. All right? We call this functional dominant problems. So here's what you do. There's 2 strategies that I have that I'm going to help you guys out with this. So notice that this is still a nice little polynomial, but this is not a polynomial. It's 3 to the x plus 1. So I gave you guys 2 examples, and I'm going to give you guys 2 strategies. For this one right here, I say let's use a chart. And you guys will see what's happening when I do the chart. So I'm going to put x squared, which is the highest degree. The highest degree in the numerator is still x squared, right? This doesn't really matter. And the highest degree in your denominator is just 3x, right? 3x. And so what we're going to do here is we're going to look at plugging in values. And so I'm going to show you guys. So let's plug in 1. So I plug in 1 here, I'm going to get 1. If I plug in 1 here, I get 3. If I plug in 2, I get 4. If I plug in 2, I get 9. If I plug in 3, I'm going to get 9. I plug in 3, I get 27. I plug in 4, I get 16. I plug in 4, I get 81. I plug in 5, I get 25. I plug in 5, I believe I get 243. What is the point of this? Notice that as x is getting bigger, right? X is getting bigger. I added 1, 1, 1, 1. Notice that x squared, it's slowly getting larger, right? We started at 1, and now we're at 4, 9, 16, 25. But the bottom goes 3, and by 5, it's already up to 243. So what we call this is we say that this function here is dominant. It's a dominant function because it's approaching infinity much larger than anything else. So another way I want you guys to think about this is if I give you 1/10, and then I give you 1/100th, and I give you 1/10,000, and then 1/1,000,000th, what is that going to? If you are to start plotting those, what am I going to? I'm approaching 0, right? This is getting really, really, really small. This is 0.1. This is 0.01. This is 0.001 or 0001. Right? It's getting smaller and smaller and smaller. So it's really important that I'm going to 0. Another way to think about this is going back to the rational functions. My denominator has a bigger function than a numerator. And all limits where my denominator's degree was higher was 0. So when your function is dominant in the denominator, it's going to always be 0. And this is one of the 2 ways to figure it out. It's usually by a table. If this had been the opposite and the numerator has been the highest function, then it would just be does not exist. Okay, does not exist. And technically positive or negative infinity, but it would just be does not exist is all I care about you guys doing. So that's strategy 1 is the chart. And we're going to talk about the chart here in example number 14 here in a minute. Well, what about this? You could also do a chart, but let's be honest with this. The natural log of 1, the natural log of 2, natural log of 3, that's not really well known with a calculator, without a calculator. So here's the other strategy that I have for you. Let's graph them. So graph them really quick. And you guys can do this in your heads, but I'm going to show you guys. So we're going to graph the natural log of x and e to the x. Again, this is one of those concepts that students struggle with remembering the graphing for. So it's okay. I got you here. So e to the x looks like this, and the natural log of x looks like this. Right? So I want you guys to think about this and visualize this. As x is getting bigger, on this function, like as x is getting bigger, notice that my function for e to the x is going in this direction. And notice that both of them are rising, but which one's rising higher? Which one's going there the fastest? Which function is more dominant? And hopefully you guys say that e to the x is higher, right? It's bigger, it's getting faster as x approaches infinity than our little measly natural log of x is. So in that case here, this is the functional dominant problem, and so this is going to be does not exist. And again, we could also say positive infinity because both these graphs are reaching positive infinity. So that's the behavior of the graphs that you would have here. All right, so that's example number 13. So either strategy works. I think most students really feel comfortable with the chart, but if you have functions that are just easy parent functions to do, just graph them and see which one's approaching it the quickest. A student did ask me one year about what about negative infinity. We would never give that example to you because negative infinity, yeah, this is approaching 0, right? That's approaching 0, so that's good. This one doesn't approach negative infinity because negative infinity is over here, right? This is actually approaching 0 from the right. So that's one of those mean questions that pre-calc teachers sometimes give students about what's the limit as x approaches negative infinity of natural log of x. The answer does not exist because it doesn't even go over here, right? It's restricted to this line. It's a brick wall, if we call it that way. So with that being said, let's look at another chart example and see if you guys are okay with it. And these are the last two questions in this lesson. So sometimes you're giving you charts, so you don't have to do anything. They're not giving you the function. We don't know what f of x is. They're telling to you, and it says, okay, well, if x approaches 5, so this is going to be from the left. So I want you guys to think about this for a second. So here's 5, and I'm approaching it from the left. So I'm at 4.5, and I'm at 4.9, I'm at 4.99. I'm approaching it from the left, and we'll get into that notation in the next lesson about left and right, the left and right hand side limits. So from the left, well, notice what's happening here. My values are going 8.2, 8.9, 8.99, 8.9999. So we're getting really, really close. So we're going to say the limit as x approaches 5 from the left, and again, I'll get into this more next class, or next lesson, I should say. It's actually approximately, we're not sure, but it's approximately at 9. And if I said, okay, well, let's look at it from the right, as you can see, we start at 5.5, and we're going down to 5.1. So we're going from the right now, and we're going 9.6, 9.2, 9.04, 9.00, 9.0001. So we're knowing that the limit as x approaches 5 from the right of f of x is equal to 9. So another thing that I'm going to tell you guys in the next lesson is that in order for the overall limit to exist, so this is previewing that, in order for the overall limit to exist, the left and right hand limits, they have to be equal to each other. They have to be the same number. So since they are both equal to 9, I can now conclude that the overall limit is also approximately that value. All right, so there we go. I want you guys to take a look at number 15. I want you to pause it for a second, read it, see if you can answer the question looking at the chart, and I'll be back with you in 1 minute to discuss it. Okay, well, I'm ready to discuss it. Hopefully you paused it. So let's look at this right here. Clearly, if we look at our values, we see we're at 2 at -8, 2.9 at -80, again, 2.99 at -800. So you guys can see as we're approaching this direction, we're looking close to 3, right? And then over here in this direction, we're looking as we're going this direction, it looks like we're also going to 3. So initially, students are like, oh, well, the answer is 3. But you got to be careful. You have to look at the values of what's happening here as well. So let's look at what's happening at x equals 3. So when we're at 2, we're at -8. And then at 3, we're at -80, right? -80. And then we're at -800, right? And then if you look at the other side, at 4, we're at +8. And then we're at 80. And then we're at 800. So you can see that this one is going that direction, and this one is going in that direction. So these values are not going towards each other. They're going away from each other. This is getting very, very, very small, and this is getting very, very, very large. So we could essentially say that there's an asymptote here at x equals 3. So this limit actually does not exist. So you want to be really, really careful. Don't just look at the x values. Just make sure that you guys look also at what's happening with the y values. Okay, so there we go with that problem. And we already know it was 3 because look at all the answers, right? They're all saying x equals 3. So hopefully that makes sense to you guys. And that is now our official lesson with limits to infinity. On the next couple pages, you guys will now have extra practice. The answer key on Schoology has all of the work for these problems just to make sure you guys are good to go. So homework is going to be to finish up these questions. I will tell you all right now that H is very tricky, And so I'm just seeing what you can do with it, but I would not expect you guys to do it in an AB class. All right, so hopefully you guys are okay with this, and I will see you in lesson number 2.